Start with is just do some more fundamental theorem of calculus. So the first thing is that there were two parts to this theorem, and the first part dealt with these weird functions and finding their derivatives. So let me get out my notes so I say it correctly. Okay, so if the function f, so if f is continuous on the interval from a to b, then the function g defined as g of x equals the integral from a to x f of t dt is continuous and differentiable and g prime of x equals the derivative of this integral is just f of x. So first of all, just make sure that you've got, I'm not going to make you like memorize all the words with this, but the technicalities about things being continuous do matter for the theorem to be true, so I have to say them. What I care is you get the big idea. So first of all, we worked with these functions like a little bit on Friday. These functions find the area under y equals f of t from t equals a to t equals x. That's what they do. They say, I'm finding the area under this curve from a specific start point to a point that's varying. So to let you find the area, suppose you have some curve, like a curve, I don't know, has watts per hour that you've used or something like that. You want to find the number of watts you used between hours 1 and 5, 1 and 7, 1 and 10. The start point stays fixed, the end point changes. That's what that function does. And what this operation tells you that for these functions, that differentiation and integration are sort of inverse-like. Do you know what I mean by inverse-like? Like you take this function f and you take its antiderivative, right? And then you derivative it. And what do those antiderivative and derivative do to each other? They kind of like undo each other, right? That's what this is really saying, is that they kind of undone each other. And there's some technicalities in that, like if this upper bound is something other than x, technically you need the derivative, you go to the chain rule. But the basic idea is that they undo each other and they kind of cancel. Okay, so yeah, some people will write this if they have, let's just do one thing and we'll move on to the second part, which is used much more frequently. If you have your function g of x is, say, the integral from a to u f of t dt, what they'll then say is g prime of x is equal to f of u times du dx. What rule is that trying to show you? This is the chain rule. Or they would say this is f of u times u prime. And if u happen to be x, then x prime is 1, right? So that's the first part of the fundamental theorem. Okay, so that part was used to prove the second part, which we use a lot more. And this says that if your function f is continuous on the interval from a to b, then how do you find the area under the curve little f of t, or little f of x, excuse me? What do you find? You found an antiderivative. It's equal to f of b minus f of a, where capital F of x is an antiderivative of little f of x.
There's no nice symbol, like the prime symbol, to show that this function is an antiderivative of that function?
No, they just use cap. Actually, the symbol that says something is an antiderivative of something else is you actually take off the bounds in the integral symbol. Like, that's the symbol that says take an antiderivative. We're going to discuss that in the next lesson. But yeah, that's the symbol that does it. And it often is the case that lowercase capital letters is a common thing as well. Now, it does matter that the function is continuous, at least at this stage in your calculus careers. If the little function inside your integrand is not continuous, you cannot do the integral. It turns out that it actually can be done, but it requires section 7, 8. You have to use limits to do it. You could really understand that, like, it's not a super, super hard idea, but for now, the answer will be if the function is not continuous, the limit doesn't exist. And sometimes this book puts those problems like embedded inside of other problems. You might get what appears to be a right answer, but it might be undefined. So the first question you should ask yourself is this true? Like, is my function continuous? Because if it isn't, you just can't do it, and the integral will, at least at this stage, not exist. Okay, so first things, find the derivative of these functions. So that's using the first part of the fundamental theorem. So that's the derivative from 0 to x cubed, 1 plus t squared dt. And this derivative rule says, take that x cubed, plug it in for t. Yep. So we've got the root. And the thing that freaks everybody out, they're like, I want to differentiate the function that's inside the integral, but you don't have to. So, and then you multiply by what because of the chain rule?
3x squared.
Very good, 3x squared. So we have 3x squared times the root. What happens to those exponents? They multiply, so 1 plus x to the 6th. And if you think to yourself, what this symbol does is, first you antidifferentiate and you plug in x cubed. You don't know what the antiderivative is, but you've done some antidifferentiation thing, you plugged in x cubed. Then you take the derivative, which takes you back to where you were, right? Antidifferentiate, differentiate, you're back at where you were. With the thing is, you've plugged in x cubed, so you have to use the chain rule to differentiate what that x cubed was. Okay, now that differentiation rule does rely upon the integral being of the form number to variable. So how can you make part B something you can actually differentiate?
Make it negative.
Negative, exactly. This is the same thing as negative the integral from 1 to cosine of x, t plus sine of t. And notice that I said equals because that still is the original function. It's not actually the derivative yet, right? When you take the derivative, much like we talked about in chapter 3 when we were doing differentiation rules, you have to tell me you've done it by using g prime. So g prime is the derivative of negative integral 1 to cosine. And that derivative rule just says plug in what for t? Cosine x. So negative cosine x plus sine of cosine x multiplied by what from the chain rule? Great, negative sine x. And so the most you can do there is that the negatives can cancel, and you could write that as sine x times cosine x plus sine of cosine x. Even if you distributed that sine, it couldn't be sine squared x because one's sine x and one's sine of cosine. So they're not the same term. Okay. And the last one is definitely the trickiest of them. So why is this example 2 that we've got there? What makes that a little bit more tricky than the preview? There's variables in both places, right? But there is this property of integrals that say if you integrate from, say your first number was a, your last number is b, pick some middle number c. If you go from a to c, find the area there, And from C to B, find the area there, you add them together, it's okay. Use the same property here. Pick your favorite number. Really, you can pick any number, doesn't matter. I always pick 0. So h is still equal to cosine x to 0, cosine of u squared du, plus the integral from 0 to 5x, cosine u squared du. And now part 2 is a lot like part A of example 1 was, right? Part 1 is a lot like part B of example 1 was, right? So before you can take the derivative of this, you have to flip around part number 1 and make it negative, yep. Which you could do in one step, like if you really understand how this works. I don't care if you can do things faster than me, because I can do things faster than this as well. It's just that that's not appropriate for class. Right. And now it's of the form where we can apply our derivative rule. So since we're taking the derivative, we say h prime so what goes in for you? Cosine x, yep, so negative cosine of cosine squared x times what from the chain rule? Great, negative sine x plus cosine of, what goes in for you in that second one? And it gets squared and get multiplied by what from the chain rule? 5. Be slightly careful with the 5x squared inside the cosine. That means 5x times 5x, which is the same thing as 25x squared. So either put your 5x in parentheses or say 25x squared. Does that make sense? So that's sine x times cosine of cosine squared x plus 5 cosine of 25x squared. So that's what h prime is equal to. And that's the hardest, really, it doesn't get more complicated than that last one. You will probably see something like the last one on your final. I'm just saying, okay? It probably will be there.
As long as it's just 1.
Yeah, it's just gonna be 1. I mean, if you can't do 1, you probably can't do the second one either, so I don't need to test that twice. They'll probably put a simpler one on there as well, so. But there will probably be one like this. Okay. The second part of the fundamental theorem is much, much, much more common, and you do use that a lot more often. So the first question you should ask yourself is the function inside of my integral symbol, that little S-shaped thing, this stuff inside the integral, that stuff is called the integrand, just so you know the vocabulary. That refers to the stuff inside of the integral. So is the integrand, is it continuous on the interval from 0 to 4? Yes, okay, great. Then find an antiderivative. So and you don't need plus c because the plus c's will always cancel. So what's an antiderivative of 1 minus 3y plus y squared? Y minus 3 halves y squared. Because just think about the 3 as, ignore it for a second. It's y squared over 2, right? What's the antiderivative of y cubed? Or just told you, y squared. Y cubed over 3. Great. And then the most tedious thing with these problems is just doing the arithmetic. Do you agree? Because you're often, unless you have a problem that's been very doctored, you're gonna have to deal with fractions, right? Okay. And then this notation with the bar means that you're going to plug in 4 and you're going to plug in 0 in the next step. So first you plug in 4. So that will be 4 minus 3 halves times 16. What's 4 cubed? Great, 64 thirds. When you plug in 0, do you get 0?
Yes.
Yes, in this case you do, but be careful because that's not always true. Like plugging 0 into cosine doesn't give you 0. Okay, so that's 4 minus, okay, to do 3 halves times 16, probably easiest to half 16, then multiply by 3, right? So what's that?
24.
24. Okay, so that's minus 20 plus 64 thirds, and there's no getting around that common denominator now. Crap. Well, it's not that bad. I think it's negative 60 thirds plus 64 thirds. Do you agree? So this will equal
4/3.
4/3. That's not what I got in my notes, but that's because my notes are wrong. Shame on me. I said that 8 times 3 was 16. What the heck? Okay. Does the process make sense though? Okay. And if you know how to find antiderivatives, like that's really just plugging numbers in. It was not that bad. Okay, so is the cube root function continuous on 1 to 8? Yeah, cube root function looks like that-ish, right? Other than I can't draw. It's continuous everywhere. Okay. So that's the same thing as integral 1 to 8, x to the 1/3. So what's the antiderivative of x to the 1/3?
3/4.
Mm-hmm.
Root x to the 4th.
I'm just going to call it x to the 4/3 for now, but you're right, it is the cube root to the 4th power. Do you guys agree that it's 3/4 x to the 4/3? So we're going to do 3/4 times 8 to the 4/3. Can I write it like this? Is it okay if I take out that 3/4? Because when I plug in 8, I'm going to have 3/4 times stuff, right? When I plug in 1, I'm going to have 3/4 times stuff, right? So the 3/4 can be taken out. All right, it'll just make the arithmetic look a little nicer. So what is 8 to the 4/3? So like Rachel was saying, it's the cube root of 8 and then raised to the what power? 4th. You could also 4th power and then cube root, but good luck.
Where did you go from 1/3 to 4/3?
Where did I go from 1/3 to 4/3? I took the antiderivative?
Oh, okay.
Okay, so cube root of 8 to the 4th?
16.
Great. So I think that 16 minus 1 is 15. So 3/4 times 15 is 45/4, right? Is that okay? Just the reverse power rule, right? Okay. So this one, is the function x to the -3 continuous on the interval from -1 to 7?
No, it doesn't exist at x equals 0.
Exactly. Do you guys agree with his analysis? This is the same thing as 1 over x cubed, just in disguise, right? So f of x equals 1 over x cubed is not continuous at x equals 0, which is within the interval. You could do that integral if I had said 1 to 7. Does that make sense? But because 0's included in the interval from -1 to 7, you cannot do it, at least not yet. You just stop and you say, you know, at this stage, I think that they're just saying D and E does not exist. I think that's all you're asked to do. And I think, like, in the homework, it'd be reasonable to explain why this function is not continuous. I will be, like, looking for that. Like, tell me where it's not continuous, and then say does not exist. But if the interval had been 1 to 7, no problem. Or even -7 to -1 would have also been no problem, right? Just can't include 0. Or can't span 0. So watch out for stuff like that. Because I'm pretty sure in the homework they're mixed in with the other problems. How about this one? Is sine continuous? Yeah. What's the antiderivative of sine? Very good. Negative cosine. From pi quarters to 5 pi halves. Okay, so we have a negative cosine of 5 pi halves plus cosine pi quarters. Hope that's okay. I just did minus a minus makes plus, right? Okay. What is the equivalent angle to 5 pi halves on the unit circle? Pi halves, yes. No, I think it's 3 pi halves. Right? Because it's 1/2, 2/2, 3/2. No, it is. You're right. You're right. I'm wrong. Yep. Top pi halves. Okay. What is cosine there? 0. So 0 plus what's cosine of pi quarters? Great. So this is just 2 over 2. Remember how I said that there's no product rule for antiderivatives? There's still no product rule for antiderivatives, okay? Like still, it still doesn't exist. Don't even try. So if you see a product, your only thing you can do is multiply it together and go from there. You have to reduce it to something you know how to handle. So, first step is to multiply the integrand. And you have to leave the bounds there because you haven't done an antiderivative yet. So that's going to be x squared plus x minus 6. I just combined like terms. Is that okay? Because x squared minus 2x plus 3x minus 6. So now can you find an antiderivative? Yeah. What's the antiderivative of x squared? Good job. 1/3 x cubed plus, and then minus. Great. From 1 to 3. So that's 1/3 times 27. No, you don't. And how about I add it, because you missed this and you haven't seen it. I'll put a plus c there and you'll see why in a sec, okay? Plus 1/2 times 9 minus 6 times 3 plus c. That's plugging in 3. Then you plug in 1. 1/3 plus 1/2 minus 6 plus c. And what's going to happen to the c's? They're going to cancel. That will happen every time, so you don't need plus c in for this stuff. Okay. So arithmetic, oh, the bane of my existence. 1/3 times 27. 9. 9 halves leave as a fraction, right? 6 times 3? And then minus 1/3 minus 1/2 plus 6. Do you agree with that?
And the reason you disregard c is because it just cancels itself out?
Yes, and that's why I've never been adding plus c to my antiderivatives at all, because it will always cancel out. Because you'll always plug in the first number with plus c, minus plug in the second number with plus c, and so they will always go away. And since the fundamental theorem said find an antiderivative, you can find the simplest one where c is always 0, as opposed to the, but there really isn't only one. Now from here, I mean, arithmetic is not my favorite thing, but I would suggest combining whole numbers first and then dealing with the fractions later. That's just how I kind of like chip away at it. So 9, negative 18, and 6. Uh-huh. Is that right? 9 halves minus 1/2 will make plus 4. And then minus 1/3, right? We still haven't taken care of that yet. So it ends up being 1 minus 1/3, which then you can even do in your head, right? Is 2/3. As opposed to trying to get a common denominator like right off the bat before like getting your like fractions that are whole numbers to whole numbers. Does that make sense? It'll be a lot faster to try to combine whole numbers and then deal with the fractions at the end, I think. Okay. Okay, in part B, there's still no product rule. Okay, still, swear. Let me know when you're ready to move on, because people are still writing. You can't see it, should I move it? Yes, no problem. Just to ask, it's super easy. I can move it in circles, but that wouldn't help so much. Okay. This one. There is no product rule, and officially there kind of is a reverse chain rule, but you don't quite know it yet. So since it's not very hard to square things, I would just suggest squaring. So first first thing you should check is that function continuous from 1 to 2? X plus 1 over x. It might have a problem. It have a problem at 0, right? But 0 is not included from 1 to 2, so you're good to go. Which is a little bit like a shame, because it's just saying does not exist would be easier, wouldn't it? Yeah, okay, so 1 to 2, x plus 1 over x times x plus 1 over x. It really is the same as the previous problem, except for the multiplication is just a little bit more tricky, right? So we'll go through it just a tad more slowly. Oh, algebra. X squared. What is x times 1 over x going to give you? 1. You see that? And then another 1, which will be 2 in the end. Yep. And what is 1 over x times 1 over x going to give you?
Over x squared?
Can I write that as x to the negative 2?
Yeah.
Okay.
Only this once.
All right, thank you. I appreciate your understanding. So that's the same thing as 1 to 2 x squared plus 2 plus x to the negative second. Great. All right. So the antiderivative of x squared is 1/3 x cubed and plus 2x. What's the antiderivative of x to the negative 2? X to the negative over negative 1, right? Which you could just make negative 1 over x, right? But the reverse power rule is you take the exponent and you add 1 and you divide by the original exponent plus 1. So just think about what is the rule for x cubed or x squared, for example, and then just do the same rule for x to any power, except for x to the negative 1, which is a bit special. And now plug in your numbers. So this is going to be 8/3 plus 4 minus a half. Do you get where I got the minus a half? I thought about x to the negative 1 over negative 1 as negative 1 over x. The same thing, right? And then plug in 1. Minus 1/3 plus 2 minus 1. Okay, so 8/3 plus 4 minus a half minus 1/3, I think minus 1. So I think 3 plus 7/3 minus a half. But tell me if you don't agree, because arithmetic and I don't always get along. Where's the 2? Okay, I did 2 minus 1, and then I distributed the negative. Yep, no problem. Yep, totally fine. So what's the common denominator going to be here? 6. Great. Let's multiply 3 by 6 over 6, and we get, what, 18/6 plus 14/6 minus 3/6. 32, I think 29/6. Do you guys agree? Yeah, okay. Oh, arithmetic, you are so tedious. And most of the stuff in this section, like the hardest thing here, other than the arithmetic just being a pain in the butt, is you need to find the antiderivative, right? That's the hardest question. Once you've got that, you're really good to go. So secant squared, I know we probably don't have that picture memorized, but its asymptotes are at pi halves and negative pi halves. So you're totally good. Remember this picture, we did graph this earlier in this semester, right? Looks something like that. Okay. So we're good from 0 to pi quarters. So what's the antiderivative of secant squared?
Tangent.
Tangent. From 0 to pi quarters. So we do tan of pi quarters minus tan of 0. And I think pi quarters is like your favorite value to put in a tangent. Yeah, I think this is just going to be 1. Because tangent of pi quarters is 1, right? Tangent of 0 is 0. Ooh, 1. Yay.
You were asking us to go past pi over 2.
And say doesn't exist. Yep, so like officially if the integral had been like 0 to even just pi halves, you would say does not exist at this stage. Or if the interval had spanned it, like suppose it had been like 0 to pi, then you would also say does not exist. And with the trig functions, if you need to use a grapher to get a picture of it, just to verify that you know what it looks like, that you're right, look back at your notes, right? Just check it. I mean, it's okay to use tools as long as you can learn from using those tools. As long as you don't blindly then forget what you just did. Okay. I really wish this function was discontinuous. But it's not, is it? Not on our interval, at least, right? Crap. Well, there also is no quotient rule for antiderivatives, just because there's no product rule, no quotient rule. Okay, so if you bring the thing up, I'm gonna do that because a lot of you, like, that's your first instinct. Okay, is that okay? Now it's a product and there's still no product rule, so don't try to make one up. Distribute, and what happens when you distribute to those exponents? They add. So that first one becomes x to the 1/3. The second one becomes x to the negative 2/3. Does that make sense? So if you do that, you're totally fine. It's just the exponents add, and just make sure that you add the negatives and positives correctly. And now antidifferentiate. So what's the antiderivative of x to the 1/3? X to the new power is 4/3. The coefficient is 3/4. Okay, what's the antiderivative of x to the negative 2/3? X to the 1/3, and the new coefficient is 3. Great. Okay, so 3/4 times 8 to the 4/3 minus 3 times the cube root of 8 minus 3/4 minus 3. So plugging in 1 just gives us those coefficients. I think we've already worked out 8 to the 4/3 at least once today, right?
16.
Okay, so 3/4 times 16 minus 3 times 2, right? Minus 3/4 plus 3. Can you find 3/4 of 16 pretty easily? Yep. So 12 minus 6 minus 3/4 plus 3. So do you agree with 9 minus 3/4? So common denominator city, this is a 36/4 minus 3/4 is 33/4. Is that okay? It's just tedious. All right. Root 2. No, you don't like root 2? Here, what would be the antiderivative of 5? Just a constant. What's the antiderivative of that constant? If I had gone from, say, it'd just be 5x, wouldn't it? Yeah? Root 2 is also a constant, right? It's just a weird one. So what's the antiderivative of root 2?
X root 2?
X times root 2. There you go. Look, not that bad. If I gave you the antiderivative of pi, it'd be pi x, right? So 1 to 4. And so I think that's then 4 root 2 minus 1 root 2, which is?
4 root 2 minus root 2.
Which is 3 root 2, yes?
Yes.
So don't be weirded out. The antiderivative of a constant is the constant times x, even if the constants are weird things. Okay.
It's a little freaky.
It is a little freaky. I know. That's why I did one like this. I knew it's easy, but you have like it's easy to be freaked out by it too. It's the same reason like I gave you derivatives of like root 2. That's 0, right? Okay. Now this antidifferentiation stuff only applies if you have like x to a power, and right now both the 2 and the x in the denominator to the power. So what you have to do in this case is break this up into the integral from 1 to 9, root 2 over root x. And just think root 2 is a constant that just kind of hangs out while you do the antidifferentiation on the root x in the denominator. See what I'm saying? So that root 2 is just going to chill. And then it's multiplied by x to the negative 1/2. And you just antidifferentiate the x to the negative 1/2, and the root 2 just factors out of that process. We talked about that with antiderivatives, right? That constants can kind of factor out of antiderivatives. So what's the antiderivative of x to the negative 1/2?
Two
2
times x to
times x to the 1/2. Do you guys agree? Negative 1/2 plus 1 is 1/2, right? And that's evaluated from 1 to 9. So you'll have 2 root 2 times root 9 minus root 1. That's taking that constant out, and then just plugging in 9 and plugging in 1 into the function root x. And I think, so root 9 minus root 1 is just 3 minus 1 or 2, right? So if you do 2 root 2 times 2, what's that make? 4 root 2. Is the factoring out of this constant freaking anybody out? It is? Okay, so here's why. So that's the same thing as 2 root 2 times root 9 minus 2 root 2 root 1. That's why it's okay. Does it make you feel better? Okay, yeah, no problem. I'm totally happy to oblige. Okay. So the next question is kind of a fun little puzzle, but it just gets at the, like, do you get the concept? So in the next one, I told you that f of 1 is 10, and that the function f prime is continuous, and the value of the integral, like the area under the curve f prime from 1 to 5 is 23, and you're going to use this to figure out what the original function is at 5. Okay, so if I gave you the integral from 1 to 5, f prime of x dx, what's an antiderivative of f prime? F, evaluated from 1 to 5, right? So that's f of 5 minus f of 1, yes? And then, do you know what this integral is equal to? Did they tell you? That's 23. So we know that 23 equals f of 5 minus f of 1. And then what else do you know? F of 1 is 10. So then f of 5 is equal to, I think 33. Okay. So a couple true-false questions, and they should be pretty obvious if true or false. So can you, when you're doing integrals, integrate sums separately? Yes, this you can do. This is true. So for example, like if you had the integral from 1 to 2 of x plus 2 dx, it's okay to do the integral from 1 to 2 of x plus the integral from 1 to 2 of 2. That's totally fine, okay? You're using that rule kind of implicitly. What's this one trying to get at? They're trying to apply some kind of integrate each things in the product separately, right? That's kind of like making up some kind of product rule, right? So no, there's still no product rule. And if it is, it certainly wouldn't be this, right? Well, not necessarily, but the product rule for derivatives was also like not f prime times g prime, right? So it's unlikely then that the rule with antiderivatives is antiderivative of one times antiderivative of the other. You could convince yourself pretty easily by doing like the integral from 1 to 2 of x squared. That's going to be 1/3 x cubed, 1 to 2, which is 1/3 times 8 minus 1, or 7/3, versus 1 to 2 of x times 1 to 2 of x. It's going to be totally different answers. So that's totally not a rule. Do you think this is okay? My instinct probably is no. And the way to really check that it's not is to pick a function and just see if you can do it. I'm just going to pick f of x equals x. So if I integrate, say, super easy, 0 to 1 root x. No, will 0 to 1 actually work? So that's, what's the antiderivative of x to the 1/2? 2/3 x to the 3/2, right? So that's going to give us 2/3 versus big old square root integral 1 to 0 to 1 of x. And that'd be big old square root 1/2 x squared from 0 to 1, which is going to be square root of 1/2. Not the same thing, right? And if you find an example for which a rule doesn't work, it means it's not a rule. Like, rules work in mathematics all the time without exceptions. And you can kind of like futz with them and say, okay, well, in these cases it works, but at least for this level, it's false if you find something where it doesn't work. This next one's a teensy bit tricky, because if you antidifferentiate and plug in 1 and plug in -2 and subtract, you do actually get -3/8, which makes you think that this probably is a true statement. But,
X doesn't exist.
yeah, this function,
X equals 0.
is not continuous at x equals 0. So this, I guess we'll say value, does not exist, okay? So, but if you do the antidifferentiation process, you are going to get an answer of -3/8, but that's not true. So just watch out for stuff. Those are trickier, so watch out for stuff like that. I think is that all in that lesson?
2 more. Yeah,
There's 2 more? Okay. Maybe I forgot. They weren't on my notes. So let's see if oh, yes, these. Okay. So this is where we're going to bring back the thing we talked about in section 5. I think it was 5.1 and 5.2. I think it was 5.1, where we found the function, and we found the start point, and we found the width of the interval. And the point with these questions is that if you limit, these sum things came from areas under curves, and if you limit this sum thing, it's the same as this integral. There was a question like this on your 5.1 quiz that you got back. So remember that this told us the width of the interval? The width was 2. What was the start point? 5. And the function is, you're taking all this stuff, it's x to the 10th. This is the same thing as the area under the x to the 10th curve from 5 to, not to 2, 5 to 7. Does that ring a bell? And so on the 5.1 homework and 5.1 quiz, I had you find the function, and you said on the interval from 5 to 7, right? So now, since you know that this is an area under that curve from 5 to 7, and you can use the shortcuts, I want you to actually find the area. So that will be 1/11. I don't know why I wrote 111, that was wrong. I just got too excited about those ones. 1/11 x to the 11th from, and I think I just didn't think this question through all that well, because 7 to the 11th minus 5 to the 11th is going to be enormous. So some huge number, whatever. But the point is that if you limit a sum, it makes an integral. And that kind of idea does come up again. Like, if you break something into chunks and limit the number of chunks to infinity, that makes an integral. And that's kind of, this idea kind of gets at that ish. Okay, one more. It's easier to solve. Okay, so what is the width of my interval? 5. What is the start point? And what is the function? Nope, just sine of x. There actually is a way to do it where you start at 0, but it's just think I'm doing something, I'm signing those numbers. And you've already accounted for the 2 by the start point. And actually the width is in 2 places. The width is both here and here. Like, both of those 5s come from the width. So that's equal the integral of sine of x. What's the start point? 2, what's the endpoint? 7. And the antiderivative sign is negative cosine, right? That's negative cosine of 7 plus cosine of 2, which is some weird number, so whatever, that's it. It is what it is.
So where are you getting a 7 from?
If my interval starts at 2, and it's 5 units wide, the endpoint is 2 plus 5.
Okay,
Does that make sense?
yeah.
Yep. Great. Okay, well, that's actually it. So let's take